This afternoon's first speaker is James Drummond, and the title of his talk is Hidden Conformal Symmetry of Gluon Amplitudes and Wilson Loops.
Okay, thanks. So I'm just going to present quite a brief review of some recent work that we've been doing. I've been doing in collaboration with Johannes Henn, Gregory Koczemski, and Emery Sokochev, the principal. And the things we're interested in are perturbative gluon amplitudes in n equals 4 Soup-Yang mills. And we're going to discuss some recent results which indicate that there are some hidden symmetries present in perturbative gluon amplitudes, which you can observe on the level of the integrals which appear there. And then in order to try and interpret what that means, we have to go through a sort of detour through strong coupling and some recent work by Aldar and Maldacena, which relates them to Wilson loops. And then finally, I'll come to discussing conformal Ward identities, which are supposed to be the consequences of these symmetries that we observe. Okay, so the basic objects we're interested in are n-gluon scattering amplitudes. We're talking about maximally helicity violating amplitudes, and in the planar theory only. Now, basic facts about these amplitudes are that they're infrared divergent, so they require infrared regularization. And they have this following general structure. You have n gluons with momenta pi, so there's a delta function for momentum conservation. Then there's some tree amplitude, which depends on the momenta and the choice of helicities of the incoming gluons. And then there's some factor which encodes the loop corrections. And this is the factor which has these infrared divergences. So we're going to use dimensional regularization with some regulator epsilon, some associated scale mu. So the loop factor, it's known that the divergent piece, in fact, factorizes into a product of things which see only two neighboring gluons. So this divergent factor, some function of the coupling, the product of the scalar product of two adjacent momenta pi plus 1, and this contains these infrared divergences. And then left over, there's some finite factor, which I'll write in this form, exponential of some fn, and this is some function of the coupling and some function of the incoming momenta. But since it's finite, I can set the regulator here to 0, so there's no longer dependence on the scale and regulator in the finite piece. So the interesting thing we're going to discuss is this Fn. Now, well, these things have appeared before in several talks already. There's this calculation of Bland, Sakon, Dixon, Kosov, and Smirnov, which used the 4-gluon amplitude calculated to 4 loops in order to extract the 4-loop cusp anomalous dimension, gamma cusp. And of course, this was used to check a prediction based on the BES equation coming from integrability. And the recent motivation for looking at these things, as I alluded to already, comes from recent work by Aldar and Maldacena with some surprising properties at strong coupling for these things. And well, what we want to do is to have a look to see if we can see any traces of integrability, by which I mean perhaps some hidden symmetries which describe these things. And hopefully then can we describe these finite parts of the amplitudes Fn to all orders. So there's a conjecture for what they are from Byrne, Dixon, and Smirnov. And essentially it says that the finite part at all orders is the one-loop part, Fn at one loop, with a coefficient given by gamma cusp. So all the coupling dependence sits in the gamma cusp anomalous dimension. And to give a flavor of what these functions look like, here's F4, which is just a very simple elementary function log squared. F5, some sum over products of logs of the kinematic variables. So S and T here are scalar products of adjacent momenta. Okay, so this conjecture, first of all, has been confirmed. Indeed, at 4 points up to 3 loops in the paper by Byrne, Dixon, and Smirnov, where they made the conjecture, and up to 2 loops for 5 points by these two groups of people. And, well, the surprising thing is, why are these functions so simple? It's not true in QCD. They're much more complicated. And also, why is the full coupling dependence given by gamma cusp? Well, so the suggestion is because there's some symmetry at work. So to have an idea of what kind of symmetry we observe, let's have a look at the one loop loop corrections to the 4 gluon amplitude. And they're encoded in a single integral, the one loop scalar box integral. So this is this black picture. You have 4 incoming momenta, P1, P2, P3, P4, and a loop integral. Now it's useful to change variables, and we're going to replace the momenta with dual coordinate variables, xi. So if we make the change of variables, we represent P1 as a difference of coordinates, x1 minus x2, and similarly for P2, P3, P4. Then we can redraw the integral, replacing the loop integration with the vertex integration. So there's some point x5, which is now becoming the integration variable. And these 4 propagators, if you draw a line through each side, these become scalar propagators in x space. So this is just a change of variables from here to here. But the nice point about this is it's possible to see from this formula that this integral, in fact, has a conformal symmetry. So the way you check it is by doing a conformal inversion on the xi variables. And then what you see is that each of these propagators, it has conformal weight at the external point, like 1, 2, 3, and 4, but also conformal weight at the integration point. And the conformal weight at the integration point of the denominator is exactly cancelled by the measure d4x5. Okay, so the integral is conformal in the dual space. And a point I wanted to make was that this symmetry is not related to the conformal symmetry of n equals 4 super Yang-Mills, or at least not in an obvious way. I'll come back to that in just a minute. Clearly, the construction only works for planar integrals. Drawing this picture will only work for a planar integral. So that's another way to see that it can't be just the ordinary conformal symmetry of n equals 4. And also importantly, since these integrals are infrared divergent, I don't in fact have d4x5, but d4 minus 2 epsilon x5. I have a dimensional regularization. And so the conformality is slightly broken by the presence of this infrared regulator. Okay, so that doesn't stop at one loop. Same thing happens at 2 loops and 3 loops. There's a 2-loop scalar box integral. It's conformal for the same reason. If I do the same trick by replacing the loop integrations with vertex integrations, again, each vertex has 4 propagators coming into it to cancel the weight of the measure. Same thing for the 3-loop scalar box. And for this integral, which is the only other integral which appears at 3 loops, they call it a tennis court integral, there's one vertex integration which has 5 propagators, but its surplus conformal weight is compensated by a particular numerator factor. And in fact, if you write it in the dual variables, it has a rather nice simple expression, which is just this one, which naturally incorporates this numerator factor. Okay, so this carries on to 4 loops, maybe even 5 loops. And the question we want to ask is what the consequence of this apparent dual conformal symmetry is. So in order to discuss that, I have to take a diversion via strong coupling, where the same gluon amplitudes were recently described by Alda and Maldacena. And there, what they do is they say that the amplitude is described by the area of a classical string world sheet in ADS5. And in order to compute the area, what they do is they make a change of variables, which in fact is the same change of variables that we just saw. The momenta are replaced by dual coordinates in the same way. They call it T-duality. And the upshot of all of this is that the quantum corrections to the loop amplitude are in fact represented just by the computation of a light-like Wilson loop in the dual X space. So, well, the infrared divergences of the amplitude, therefore, end up being mapped to the ultraviolet divergences of the Wilson loop. And furthermore, the amplitude, under this prescription, inherits a conformal symmetry from the Wilson loop. So we know the calculation of the Wilson loop in n equals 4 super Yang-Mills has an intrinsic conformal symmetry. Because of the ultraviolet divergences, that symmetry is again broken by the regulator. So inspired by this, the question that we asked ourselves is whether or not this correspondence could also work at weak coupling. And it turns out that, in fact, yes. We checked it at one loop at 4 points in this paper. Very shortly afterwards, the one-loop calculation was generalized to endpoints by Brandhuber, Heslop, and Travellini. And then, more recently, we did a two-loop calculation at 4 points, and earlier this week, a two-loop calculation at 5 points. And in all cases so far, the Wilson loop agrees with the gluon amplitude. So now, once we have this Wilson loop picture, if we believe that the amplitude is represented by a Wilson loop, we can now try and discuss what the consequences of the conformal symmetry, which we observed in the loop integrals, can be for the amplitude. So if we just focus on the Wilson loop for the moment, what we can do is we can exploit the conformal symmetry to just derive a Ward identity based on the special conformal transformations. So the Wilson loop also factorizes into a finite factor, which I'm again going to write as exponential of Fn. And it's the same Fn because it turns out to be the same Fn for the gluon amplitude, times some ultraviolet divergent factor. And this ultraviolet divergent factor is going to induce some anomaly in the transformation law of the special conformal transformations. Okay, so that translates into a differential equation, a Ward identity for the special conformal generator K on the finite part of the Wilson loop. And we end up with this differential equation. Here's K on F is given by an anomaly governed by gamma cusp again, and a very simple anomalous term. Okay, so given this Ward identity, it turns out that in fact it's extremely powerful. If you look at the 4 and 5 point Wilson loop, which correspond to the 4 and 5 point gluon amplitude, this differential equation actually has a unique all-loop solution. So you find precisely for F4 this gamma cusp coefficient times this very simple log squared function. So if I took the function for the gluon amplitude, log squared s over t, and if I transform s and t into the dual coordinates, this is precisely the expression I would obtain. Similarly, for the 5 point Wilson loop, I again hit exactly the expression for the 5 gluon, finite part of the 5 gluon amplitude, again with coefficient gamma cusp. Okay, so 4 and 5 points, there's a unique solution. Starting from 6 points, the solution is no longer unique. And the reason for that is because you can form conformal invariants from the 6 points that are making the cusps of your Wilson loop. So you have to go to 6 points to do this, in fact, because there are constraints on the separation. The momenta of the gluon amplitude are light-like, so the sides of the Wilson loop are light-like. So in fact, only when you get to 6 points can you form these conformal invariants, these cross ratios, and there are 3 of them. So from 6 points and beyond, you should expect that the solution of this conformal Ward identity for the Wilson loop will contain an arbitrary function of the cross ratios. Okay.
I understand your argument. So the right-hand side of the equation you're solving, how do you get that?
This anomaly. Okay, so what you have to do is you have to imagine considering the path integral for the Wilson loop. You make a conformal transformation on the Wilson loop inside the path integral, and you will obtain the fact that the conformal variation of the Wilson loop is governed by the correlator where the Lagrangian is inserted together with the Wilson loop. And then you have to integrate that dx, d4x, x mu. So that's this, well, what I've written here is the equation for the finite part, but if I were to just do k on w, the right-hand side would be this object that I just described. So then what you have to do is argue that there's a particular constraint on the form of the divergent terms in that correlator. So when you make the conformal variation, this anomalous term appears with a coefficient epsilon in front of it, because the action is no longer conformally invariant because you regulate it. It has an epsilon non-conformal invariant. So you're only interested in the divergent term of the anomalous variation. So you need to compute this and argue about the structure of its divergences. And if you do that, you conclude, in fact, that once you boil everything down and you hit this thing on the finite part, this is the structure which remains. Okay. So I would guess yes, but I don't know how to prove it. I mean, it looks like it, right? Because you have a first order operator acting on Wilson loop equals an anomaly due to the cusps. Oop. Okay, so I should say for 6 points as well, the BDS ansatz for the gluon amplitude is still a solution, it's just not the unique solution. So if you like, the general solution for the Ward identity is BDS plus this arbitrary function of cross ratios. Okay, so I'm nearly done. Okay, great. So, so there are three basic scenarios then, given what I've told you so far. So one possibility is that this, in fact, it's just true generically that Wilson loops and these MHV gluon amplitudes are the same as each other in n equals 4 super-Young mills. So that's kind of the most optimistic scenario. If so, then certainly the gluon amplitudes will have this dual conformal symmetry, just because we know the Wilson loop has a conformal symmetry. And the conclusions from that would be then that the BDS conjecture would be correct for 4 and 5 points to all loops. But it might receive corrections from 6 points and higher, and in fact that appears to be necessary to match a recent prediction of Alda and Maldacena about the form of the n gluon amplitude at strong coupling for n large. So, well, if it is true, then the question is, where does it come from? We have these unexpected, potentially non-local symmetries, which appear in the gluon amplitude. It's very suggestive of a relation to integrability. The next sort of middle scenario is that the duality between Wilson loops and gluon amplitudes is not actually exact. It just happens to be true when we look at it at low loop order in perturbation theory and exactly at strong coupling, but somehow in between the two things are allowed to differ. In that case, it's still reasonable to conjecture, based on the fact that we can see some kind of conformal structure in the gluon amplitude at weak coupling, that it's implemented by the same conformal Ward identity. And if that were true, then again BDS would be correct for 4 and 5 points to all loop orders, and it would agree with the Wilson loop, but only because they're forced to by symmetry. And for 6 points and higher, the two things could disagree with each other, and either one or the other may still coincide with the BDS ansatz. But if that's the case, if you don't have the Wilson loop equivalence, then you have to answer the question where the dual conformal symmetry comes from. So that would still be a mystery. And then the least optimistic scenario is that even this symmetry, which we observe is somehow a low loop accident, only happens mysteriously up to 4 loops or 5 loops. And in that case, then you should expect that even the 4 and 5 point gluon amplitudes would disagree with the BDS ansatz at some loop order. And in that case, we would have to ask ourselves why it's mysteriously restored at strong coupling, because this calculation of Alda and Maldacena find agreement with the 4 gluon amplitude. So, well, the most urgent thing to do next is a comparison at 6 points of these gluon amplitudes, Wilson loops, and the BDS ansatz. And then if we know how these things look, we'll have a better picture of what's going on. Okay, thanks.
So your sort of claim that the 6-point function must have the function of cross ratio. It's actually a function of cross ratio and coupling.
Yes.
So instead of one function of coupling, which is, you'll have infinite number of functions.
Yes.
parameterized at 6 points?
Well, infinitely many. It depends how many functions of cross ratios appear. But yes, in principle, infinitely many. Yeah.
Function of two arguments is
Yeah. Okay.
There's additional constraints from polynomial limit. They're not just arbitrary functions.
Right. Okay. There, yeah, indeed. So this word identity is not necessarily the only constraint on these functions, but in principle, still yes.
Further questions? If not, let's thank James.